Well, thank you very much for being here. Thanks especially to the organizers, in particular because of their patience when circumstances were anything but clear. I could be here. I really had a great week, so thank you very much for that. I noticed this week I'm surrounded by physicists, and I used to be one, but now I work in math. So I thought about making a small presentation on some recent work with my PhD student. I mean, time allowing also with a research group. We still don't have the paper out, but we're writing it on these things called NIM-reps. So I thought about starting with a dictionary. That usually helps. I will try to be as pedagogic as possible, given the different disciplines. So let me start with some background and motivation. And first thing, dictionary, hopefully Pictionary at some point. So, I mean, the general setting I'm going to be working on is rational conformal field theory. So let me just clarify a couple of things there. Sorry? Anything so you follow me. Usually it's denoted in physics, the higher algebra. So this algebra that controls all the symmetries on the CFT. Usually in mathematics, we work with vertex algebras or vertex operator algebras. Sometimes also lately, these W algebras. So quite baroque structures. Not really intuitive, but the beautiful thing is that they really encode all the information of the CFT in their structure. So let me call one of these new. By rationality in here, I mean that if I take representations of this algebra, so modules over this algebra, this nu has a finite number of irreducible representations. In this case, meaning that you cannot break it out in smaller representations. So let me just give them a name like phi 1, phi 2, whatever. Another important term, and I really couldn't figure out what's the most common way to refer to. So the fusion algebra or fusion ring, but I also saw it was called Verlinde algebra. I wasn't completely sure. This means mathematically that we have a fusion ring, and this tells us how to multiply together these phi's two. So normally when you have a chiral algebra very well behaved, and that means it's rational and also satisfies another extra condition. Usually it's called situ confinedness, so it's a little bit technical. Usually, BOAs, what to say. So usually you can take a certain category out of the representations, and that's going to be something called a modular tensor category. I will. How familiar is everybody with categories? Do you have an idea? Shall I give a small appetizer on that? Maybe it's a good idea. So, let me just say that there's these modular tensor categories, MTC for short. This is a basic independent formulation of the Moore-Seiberg data of the CFT. So like it really takes all this in a basis independent setting. And so it gives us perspective on like, how is everything behaving using these guys? So let me just spell this out for you. I mean, when I talk about the category, this means that I have a collection of objects, say a vector space, a module over a ring, a manifold. Like really, I mean, I like to say most of the mathematical entities you can think of, any mathematical concept can be put into a category. Number theories will not be happy about that, but okay. So in this case, for example, back. And then the key thing is to have a way to connect each other. So in the case of vector spaces, you have a linear transformation jumping from one to the other. If you have two modules, you have, I mean, a module homomorphism, you know, whatever, depending on each case. Of course, subject to like certain compatibility conditions. So like everything, you know, if you compose two morphisms, this needs to be happening correctly and so on and so forth. So and of course in this, I mean, whenever you have a category, you can put like an enormous amount of structure inside. So, I mean, in the case for the modular tensor category, I mean, of course, I'm assuming quite a bit of finiteness conditions. Like, for example, if I have two objects, I mean, and then any morphism I can define between those two. I mean, if I count how many of those I have, they have to be finite. That's finiteness. I'm also assuming this finiteness of objects. I mean, that's called semi-simplicity. I can tensor. So like I just like whenever you have two vector spaces, you can multiply them with a tensor product. I also have, just like with vector spaces, you have duals. So whenever you have an object, you can define some sort of analogous notion of duality. I have like this extra thing of, I mean, just two extra conditions here. So there is a special object, which is going to be called a unit. So like whenever you multiply it with any other object, you're going to get back the same object. That's part of what is called a monoidal structure in here. And in addition, I have a non-degenerate braiding. So like if I have two objects, there's a way of relating that to, I mean, two objects and I multiply them, I can relate them with, when I take the two objects, opposite direction and multiply them. So that's what is called braiding. Well, you can guess where the name comes. And this kind of, I mean, in physics, this accounts for like the braid group when you go into two-dimensional, I mean, to account for all this statistics of two-dimensional field theories. So this is a lot of structure, but actually it appears supernaturally, I mean, in CFT, when you have one of these BOAs that behaves very nicely. And actually one of the topics nowadays is like, what's the best way to lift like for many of these finiteness conditions, and what's a good generalization of an MTC. But okay, but back to the thing. Yeah, Andy? Yeah, I mean, these things, I mean, this is just a category, and then add all these conditions. There's like quite a lot of these. I mean, I'm skipping and just trying to make it as simple as possible for the sake of understanding. But like, this is a category. This is what makes it modular tensor. Okay. Let me add a couple of extra things to the dictionary to conclude it. So simple currents in here. these are going to be objects in, so if I call my category curly C, that they need to satisfy two things. One is simple, so we cannot be broken into smaller objects. And something called the quantum dimension. So it says a notion of dimension for objects in a category. This needs to be 1. I mean, just take that as some sort of dimensionality condition. So using this, guys, usually you can construct what is called an algebra object in a category. And it's really the natural notion. So if you have an algebra over a field, take that to the categorical setting, you have exactly the same structure. So it's one object, you need a multiplication, you need a unit, and then associativity and unitality need to follow, just in the categorical context. So, and this, yes. That object is simple means that you cannot break it down in smaller objects. So just like take a vector space, and you can, I mean, if you don't reduce, just if you cannot, the simplest thing you can have is just K. Exactly. So, and using these objects, let me just conclude. By the way, this dictionary is really roughly speaking, but so if I have one of these objects in this category, I can construct A modules. That will be the boundary conditions. And the defects will be the A by module. So in particular, the algebra object is a boundary condition itself. Okay, so given this setting, I would like to spell out some key ideas that start this project with Sam. So back in 1999, Roger and friends, so Beren, Pierce, Petkova, and Zuber, they proved the following really interesting result. Suppose you have boundary, rational conformal field theory, and boundary because you're going to be working in a cylinder. The thing is that when you introduce this boundary, I mean, of course, there's some compatibilities to check, I mean, given by the Cardy equation. The thing is, what they proved in this result, it was like solving those equations was exactly the same thing as actually finding what it's called the non-negative integer valued matrix representations of the fusion algebra. So I mean, just that. I mean, oh, I mean, like solving one thing, I mean, it's exactly the same thing as testing the other one. I mean, like testing and finding the NIM-reps. So. And then, I mean, actually, NIM-reps have been studied in a number of cases. So, like in this same paper, they analyzed the case of SLN at the level 1. Then later, like Evans and Gannon showed, I mean, I also found that NIM-reps for like SLN2 at level 2 and SON at level 2. More recently, back in 2021, Dye, Evans, and Matthew Pugh, from our colleagues from Cardiff, they also computed the case of SO3 at the level 2M. So like there has been some systematic study of these guys. So, okay, tell me, Chris. I mean, I'm going to define those in a second mathematically. So if you have 1 minute of patience, I mean, I can just write down exactly what that means. So, yeah, so, okay, so that's one key point. So, I mean, BPPZ, Gannon, then Evans and Pugh. And then in parallel, well, these categories over here, the modular tensor categories, they have been studied quite intensively recently, in recent years. I mean, like so far we have a very nice classification until, I think right now we're like at rank 6. So when we have 6 objects, we know exactly what to find and how they are, how they behave, all the data that we need to like fully understand those. And analogously, I mean, well, in parallel, we also have been studying them in the fusion ring. So in that actually we have a very good grasp of how they look like in higher ranks. So So, for example, I can mention this recent paper, I think it was like by Eng, Rowell, Eric Rowell, and Wang. When was this? Yeah, in 23. So we have like a clear idea of what happens all the way until rank 11. So like already we're at very big rings over here. The thing is that, I mean, when you go and classify these fusion rings, you find several different families, I mean, that appear just because, I mean, of the structure. And so, for example, we have what is called pointed categories. So that means that the fusion ring behaves just like a group. So like whenever you multiply these two, I mean, like you multiply them following the same groups, I mean, the same rules as we will have in a group. And actually, I mean, the pointed case is particularly interesting because there are some of these VOAs, I mean, in particular the case of the even lattice VOAs, that actually you can construct, I mean, one can prove that if you take one of these lattices, you can produce a modular tensor category, which is pointed. So like, I mean, there's some extra motivation from the VOA side in there. Another,
Can I ask you a question?
please.
When you mean that it's a group, you mean that if you take 2 reps, you multiply them,
You multiply them.
you get another reps, or,
Mhm.
rep, or you get...
No. You stay in there.
Oh, you
It's
stay in-
closed.
Okay. So,
Okay. So in this case, I mean, which is you absolutely necessary needing here in the pointed case. I mean, because you need closeness for the group. So I mean, and everything behaves like a multiplication. So sorry, like in a group, when you multiply, you need to have an inverse. You have, of course, you need to have this neutral element, which is exactly this guy over here. So and so on and so forth. So yeah, thank you. Near another important family near group. So it's like we have the previous case, it's a group. So what happens when you add to that group something else which is not invertible, doesn't behave like a group. So that's another important family. It's also relevant because it's related to, I said here, lattice VOAs. VOA mean vertex operator algebra. This guy's bound there. Near group is related to some categories which are called Tambara Yamagami. So you need the group to be abelian, and then you need some extra condition on the near. I mean, just to go into that case, Tambara Yamagami, they're really relevant in mathematical physics lately. I mean, they have appeared in several things related to orifals and TFT. I mean, 2+1 TFTs, and so important guys over there. So we were like, yeah, great. So everybody, all these people have been working in different examples. So Sam and I were wondering, okay, what happens to the NIM-reps in here? Up there. So question by Sam and I. Well, the NIM-reps for those, we also included one more quantum group-like one, a little bit more complicated. And our main motivation for us in here to perform this program is because of the following. We wanted to, we have been working for a long time on certain projects that wanted to classify these guys at different categories. So, computing which ones, when do we have an algebra? What kind of properties do they have? If you give me a category, any category, that's tricky. It actually requires a lot of work, and I have been involved in a number of projects to do that. But something that I was wondering at that point, it was like, okay, I have, if you give me a category, how can I sweep, really? Like, when am I going to find what's the shape they're going to have, and so on and so forth. And we found the reason to study the NIM-reps, it's because we found a way to compute these algebras through the NIM-reps. And that was like, boom, straightforward recipe to detecting everything that can be in there. Well, almost everything, but of course, given certain conditions. So why? So, just to mention, there are some classifications that we did back in the day. So with G.V. Morales and Monique Müller, Julia Plafnig, yours faithfully, Angela Tavira and Chelsea Walton. This is a Woman in Representation Theory 2 collaboration. So we performed one of these classifications, and we recovered, this was in the case of group theoretical which is like a slightly fancier case than this one. Sam Robert Lowitz from the University of Nottingham. We also discussed the case of Dijkgraaf Witten categories. So like, again, relevant for the physics. And then we performed like classifications in there. But we had so much cohomological fun over there that we were like, okay, we need a way to spare the pain, however, in some way. Chris, you look confused. Sure. Mm-hmm. No, I mean, you do know the simple objects. What you do not know are the algebra objects. And that's what I would like to find. Well, I mean, that you can, I mean, of course, I mean, you can construct algebra objects out of simples. In particular, you can construct algebras out of simple currents. So, I mean, but it's not the only way. So, okay, you start looking happier. Let me. Well, not really. I mean, like, there's many, I mean, if you, in particular, if you want to, I mean, you do know the objects, you knew the morphisms, more or less. But now you want one object that needs to have two particular morphisms attached to it, so it behaves in a concrete way. And then things start getting funny. I mean, and just saying an algebra object. Then you can also request things like Frobenius. Do you want it to be Hopf? Do you want it to be separable? Do you want it to be, I mean, like any kind of, well, weak Hopf or quasi-triangular Hopf or all that. I mean, that gets more complicated. So what we figure out, I mean, like finding an, I mean, of course, an easiest example I can give you of an algebra object is actually this unit, this one. Because, well, I mean, like, it's really really trivial one. But I mean, if you want to find something more, that's actually more, I mean, as categories become more tricky, bigger, and so on and so forth, then this question becomes and actually it's quite a problem. Well, it's part of a larger program. So like all these tensor categories, I mean, they can be seen as a ring, and you can construct modules over those rings, which are called the module categories. Classifying those, it's straightforward related to classifying these algebra objects, and that's like less than trivial. So, I mean, it's not as straightforward as it seems. I mean, like having all these conditions extra attached, that's where things get interesting, funny, painful. Put your adjective. Happier now? Hopefully. Are you with me? That's the important part. Yay. Okay, where's the eraser? Oh, here. I feel like I'm gonna regret erasing this, but okay. Okay, that's where. Tell me. I have my notes, but yes. Okay. Right. So, you know, all this to say we're interested in that. We want to compute them. Here we go. And then I would like to tell you a tiny bit on the mathematical, sorry, it's going to be boring, definition of an NIM-rep. Hopefully, quick intro to the NIM-reps. So to start, this is going to denote like positive integers with 0. So I'm gonna write down RB for a fusion ring. I'm gonna use your physics intuition on this, and then say that So R is going to denote the ring itself. And this B is going to give me a basis for the ring. I'm going to denote it like this. This set, this is finite. Sorry, let me write. I'm jumping ahead of myself. Basis with 1. And then this is going to be a finite set with a certain involution. I'm going to denote as that. So if you give me a ring, a fusion ring, don't move. What I'm going to do is to to construct one module over this one in such a way that when I act with the elements of the basis of the ring, then everything I get is positive coefficients. So positive integer coefficients, and that includes 0. Okay. Does that help with the intuition, Chris? Yeah, I'm not completely sure. I'm chickening out behind the math. I'm not completely sure. I mean, like, why that should be. I'm guessing that if you want, I'm guessing that the solutions of the Cardi equation need you to put the restriction on the coefficients in front of them. If I remember more or less correctly, and I'm guessing correctly from what I remember of the paper, but I may be wrong. Please feel free to correct me. Oh, bingo. Wait, are they? Yep. About what's the physics reason behind that, I'm not totally sure. Well, for my physicist, that is as long as it can go. Makes sense. Yeah. Oh, bingo. Okay. All right. Okay, let me just write the definition. So, NIM-rep. So, Yep. It's modular. Yeah. If I remember. Yeah. NIM-rep. So, module over R. So we're going to call it A. With a basis that with the basis of the ring as follows. So norm of we. Yeah. So if you have an element in your basis of the ring and an element on the basis of the module, then if you act on it, then you would just bless you. What you're gonna get is a certain combinations of element of the basis of the module, and these guys over here, they're gonna be in there, and there's a certain rigidity condition. So that needs to reconciliate like this involution with the action of the modules. But let me just leave it there for a simple idea. Examples. That always helps. So for a fusion ring, let me remind you one of my favorites, so like the icing one. So you have B is 1, X, and Y, and you take the integer span of that. So, I mean, the addition is just defined linearly. And the multiplication is given by the Ising fusion rules. And this is given by, so x squared gives you 1 plus y squared. Y is squares to 1. And then xy, yx is equal to x. So if you take then this pair said B and B, this is a fusion ring. And if I want to give you an NIM-rep, sorry, yes, you're absolutely right, thank you. And I mean, if you want an example for a NIM-rep, actually a fusion ring is a NIM-rep over itself. And I'm not giving something fancier because, well, some are coming, some examples are coming. So using this, I mean, this idea that we're just dealing with modules over a certain ring, you know, you can just define direct sums of modules, like the most intuitive way. You can also define products. You can also define sub-NIM-reps in the same way. So because you have a module, so you will need a sub-module that respects everything. So in that way, I mean, we can simplify a bit things. Oopsie. No, that was a bad idea. So we can easily define direct sums, sub-NIM-reps, and so on. And in particular, I want to define a couple of things, what I mean by an irreducible NIM-rep, which is the case when we don't have any proper sub-NIM-reps. So like you can break it down again in smaller pieces, in smaller NIM-reps. And that's one. And then I want to define how to actually connect the NIM-reps between one with each other. So how do we define an isomorphism? So if you give me A and M, A prime and prime, so two NIM-reps over over a certain fusion ring R and B, a NIM morphism. This is a function that goes from one basis to the other that induces, oops, Z linear map between A and A prime. So like just connect the bases, then the module will follow behind. And if you have, if this function over there is a projection, then you're going to have an isomorphism of NIM-reps. So like there's a way of identify them. And Andy, how am I doing with the time? What? But I was instructed 1 hour of a talk. Okay. Okay, because I was thinking about skipping some parts and okay, well, I can just, well, but first, is everybody with me? So how are we doing? I mean, I think, I hope I convey the idea. We want to find these NIM-reps. They are just modules over diffusion rings. You can construct direct sums, direct products, sub NIM-reps, and so on and so forth. Two important things: how to connect it in two NIM-reps, so we can compare when they are isomorphic. This is the way to do it. And one important one, irreducible ones, those that we cannot break in smaller NIM-reps altogether. No. I think they are combining. When I was reading the paper, I mean, any solutions were written in Ishibashi states, in terms of the Ishibashi states. So I want to think that somehow they're written in terms of these, depending on the basis you use. I'm not completely sure. I wouldn't say so. Yeah, but I'm not completely sure in here. I mean, probably they are. I mean, like if you're using the basis to write those down, probably they are. But okay, I'm not completely sure. I mean, so what I remember from Roger's paper, I mean, like they were just writing down in terms of Ishibashi, so not completely sure what happens in the Cardi paper. The basis, right? Yeah. So the basis of the NIM-rep, I will try to guess. Yeah, makes sense, because then you can write down like every element in your NIM-rep in terms of those and that. Yeah. So I think makes sense. No, I mean, this is a great exercise. This is exactly why I was planning this talk like this, because I really want to gain an extra intuition on this, because there's some questions like for everybody. I mean, please help me out understanding some things that are going on here. I'm not sure. I don't know. I mean, like, that's as far as I can do with my physics from 10 years ago when I left. So yeah, maybe. Wait, but then now I'm confused. Like, well, but then how do you do? I mean, wait, okay, yeah, okay, yeah, yes, makes sense, makes sense. With an NIM-rep? Yeah, I mean, like you can have different algebras in there. And what we do, what we do is like write down the NIM-reps and then extracting those out of it. And it can be more than one. I mean, there can be different cases. So here's a big spoiler. Remember that I was mentioning like the pointed case of MTCs where you had your category that where the fusion ring behaves like a group. So in that case, every algebra, and we knew this from before from some work by Ostrich and Natale, we knew in that case that every algebra object is going to be given by a combination of symbols which are labeled by the subgroups of the group. So, and actually we when we did this was like our first case because we knew what we were going to find, and we find exactly the same thing. In the case of near group, you could have different cases of algebras in that one, and so on. So I hope I'm convincing you. No, in the Ising case, if I remember correctly, you just have one algebra and it's given by the group inside Ising, which is set to. So if I remember correctly. Okay. Yeah, I don't know what's best for 40 minutes. So how would you, will some pictures help on all this? Okay, let me just introduce some visual language for this. So suppose you have an NIM-rep, of course, over some fusion ring. We can construct something that we call the NIM graph. And actually, they in Roger's paper, they mention this quite a lot. The fusion, I think they call it the fusion graph. I'm not completely sure if this is exactly the same thing, but okay. The NIM graph is constructed by drawing. So for for every element that we have in the basis, we're gonna have a node. Of M, and then I'm going to write an arrow, a directed arrow, with source MI and target MJ, these two inside M, labeled by an element of the basis K, BK. For every time that MJ appears when you act with BK on MI. So it's a little bit strange. I mean, when you look at it first, but actually it makes sense. An example, because I hope that helps. Actually, I can follow up in here. So remember, we need to put a node for every element I have on my basis. So I have 3 elements, 1, 2, 3. X, and another one corresponding to Y. And now I need to look at the fusion rules. So, okay, If I act, with y, on 1, I'm going to get 1 arrow on this direction. If I act on y with y, then I'm going to go back to 1. So this is y. And in here, similarly, if I act with x, I'm going to get an arrow in this direction. If I act with x in here, I'm going to have an arrow this direction and this direction. And then I need to account for this extra fusion rule and go. And that will complete this. So this is x, and let me just put it like this so that you distinguish. So this arrow is x, and here this another y. And that will be the NIM graph of my NIM-rep. Okay? You could construct it like that. And to distinguish from the y, so it's clear that, you know, you're labeling them with different elements of the basis. Okay? And actually using these NIM graphs is really, really practical. To see the reducibility of the NIM-reps, because if you have a connected NIM graph, then you know that this NIM-rep is going to be reducible. Let me just write that down for you. This is like if and only if the NIM graph which is really useful when you're like, you know, you're computing the NIM graphs, the NIM-reps. You want to see if there's any kind of sub NIM-reps and so on and so forth. So just picture, and then you see if there's anything to put out in there. Okay, so once we have these graphs, we want to, I want to tell you a little bit about the recipe to extract the algebra objects. Once we have one of these graphs, these NIM-reps and these NIM graphs, I'm going to do a little bit of a black box, but because I don't want to bore you with the mathematical details, but hopefully, let's see if we can. And I'm going to define an NIM-rep is what we called admissible if there exists a certain element of the basis of the graph that so that if you have any other element in the basis of the NIM-rep, you can always connect this element with M0 using one element of the basis of the ring. Let me just write it down. It's like, I like to think of this admissibility as some sort of like extra connectivity in the graph. So like you have one element in M, you can always go to another one if you use, an appropriate element of the basis somehow. Bj, if you act with Bj on this M0, then you can always jump to Mi for any element that you have in M. So using that, using these admissibles, sure. You need to have a special node out of which you can reach any other node if you use an appropriate element of the basis of the ring. So it's like it's some sort of like special one that allows you to jump to like any other point. As long as there is one, done. You're there. We're good. We're game. Okay, so let me just make some extra space in here and then tell you how we extract the algebras. So for I'm gonna so if you give me an admissible NIM-rep, any algebra objects you may find are going to be, you're going to see them from the graph. Any algebra objects will be of the shape AI, BI, where, so, I mean, like, this is, again, elements of the basis of the ring. So this is B, but the important part is this guy here. This AI is the number of self loops of M0 that are labeled by BI in the NIM graph. And that here comes my first physics question for you. What are we doing here? So what does this procedure? Please. I mean, you have, well, you have one object, which is the unit. So because you have, that's one listed subgroup of set 2, 1. And then you will have another one, which will have, I mean, which will be labeled by 0 and 1. So like the 2 elements of set 2. No, I think, did I, oh, come on. Did I erase it? Ugh. Let me show you. I mean, I have prepared a couple of extra that where you can see it this like a little bit nicer. If you don't mind seeing those. Okay, on the physics. So actually, so. No, not this one. Oh, sorry. Yes. Okay. It should be. No, I mean it's set up my iPad. Hopefully 1 minute. Okay.
Going in the direction of the draw the NIM graph. We just drew the multiplication by x and by y.
Yeah.
We didn't do with the that.
No, I mean, of course you should, I mean, we don't, I mean, in NIM-reps, that's probably something I should have mentioned. We don't include action with one just to avoid overloading of the,
But it counts in the sum.
uh,
Each of the action of one will produce a self.
yep,
So
yes, it does appear in there. Yes, I mean, because you need to put it on inside the algebra. By the way, this is not working. Oh, here it is. Great, great. Okay. I hope you can see that. Let me probably. Okay, I want to take one example of the NIM graph and how to look at the algebra. So let me take just decline 4. So you have, remember these are the fusion rules. And then it has 3 isomorphism classes of subgroups. So one is when you take the group, the subgroup is just the group itself. I think I'm jumping a little bit ahead. But for example, here you will have the algebra object will be given by 1, 2, 3. So like that's, yes, and the identity. So AI. Okay, let me try to help that. How are you choosing M0 in the label by BI in an graph? I mean, sorry, what? In here, I mean, you need to take into account sorry, Susan, I'm not sure what you're not seeing, so like I'm trying to.
For example, in the icing, there was only in the NIM only one self.
Yeah.
Because we didn't do that. So this AI coefficient.
Yeah.
Will also be equal to 1.
Yeah.
For some specific case or 0 because there are no subgroups. Or if you can do that.
No, I mean, like you need to count the identity. I mean, by the way, the basis here, you have 1. I mean, it's a basis with 1. So that enters in there. So, and then you will need to count the extra loops over there with 1 to get the algebras. In this case, sorry, I'm a bit confused. How can I? I mean, in this one, you have. Hello? Yeah. Sorry, A1 is A1. Sorry, how are you assigning A1 or what? Yeah. Yeah, but entity ABC. Yeah. So 1. Yeah, there's 1 for, and then you have one copy of each, and then you will have 1 plus 1 copy of each of. So you will have like every element of the subgroup in the algebra. So like 1 element for the basis of, for 1 element each, every element in the basis will be in the algebra in this particular case. In this case, yes. I mean, like in some other cases, not necessarily. Back to icing. So, I mean, what are you choosing as M0 in there? What is M0 in that case? So, I mean, in there, well, let me try to draw it again. We had, I can do it. 1 second. So we had one here, so that's y. One here, that's x. And then you will have, that's x. And then we had here y to account for, I mean, like the extra how x and y interact with each other. Okay, so we need, I mean, in order to have admissibility, you need to, to see what M0 is. So you need to choose one specific node in each case in here that allows you to go to any other node. I mean, if you act with any element of the basis. So suppose you take this, you can go into here. Suppose you can also go to here if you multiply. Same here, same here. So actually there's there's more than one choice of M0. So that means this is admissible. Okay, now that we're here, now M0, suppose that you have self loops in here. Of course, you need to take the 1. And here depends, you need to take, so let me account for that. So you will have B1, and then what else do you have? In this particular case, what was it happening? What is happening? Okay, well, the only case we have here something is in here. So, and you need to, you can choose this one to be M0. You need to account for this self loop, and that the label is going to be this one. So you will have this. Does that make sense? And it makes sense because this B1, this Y, this was the element of the basis together with 1 that makes set2. So like you're taking every element of the basis, every element of the group to produce the basis. So every element of the basis labeled by the group to produce the algebra object. So this is yours. This is your guy. Yeah, I'm just 0 for it to account for the 0 of the group of 1. Oh, I think it's neater. Okay? Happier?
If I take M1 as M0, don't I only get B1?
Yes, in this case, in this case, you only have this one.
Yeah.
So, yeah. Because you don't account for this, but that's why I was saying before, it can happen that you may have more than one algebra object. And then, to account for every single choice that you may have in here. Okay? Are we happier? When you choose here, and if you choose in here, I think you will also have. Yeah. Yeah. You get some B1 and something else. Okay. So yeah, now going to the question. What's the physics behind this thing? Because we cooked up this recipe like using category theory, like a little bit more advanced than I'm explaining here. And well, it's actually nothing too complex. Not exactly very sophisticated. It really allows for like a very nice proof. But the thing is that one question I'm wondering is like, what are we doing on the physics side? because what we are taking is like take the fusion ring, compute the NIM-rep, and then extract the algebras in there. So what's going on in here? Is there like a physics way of detecting these algebras in here? Go ahead. I guess, yeah. I mean, it should be some, I mean, at the very least, it should be some boundary condition. But I don't know exactly. I mean, well, no, I mean, like, okay. I mean, in that, following the dictionary I was saying before, yes. I mean, because an algebra in particular is an A module. And I mean, in this case, it will give you a boundary condition. But I mean, like, I'm wondering something more on like, what exactly are we doing to the fusion ring so that we actually can extract the algebra objects in here. By the way, one subtlety I haven't mentioned is that we are able to guess the shape of the algebra, but we are not able to describe in detail how these algebras are going to look like. Sorry, like how the structure maps of the algebra are going to look like. And that's something that because of this procedure, I mean, like, usually you can guess, well, you can make some guesses on like how the structure maps of the algebras are going to look in the category. But in this case, we're like somehow taking perspective. And in that step, I mean, I'm going like at the level of the fusion ring, forgetting about like all the cohomology, the constraints, the structure below, and consequently the structure maps we may get. So like we lose some information there. So another question I had in here is actually that, like, what are we doing so that we can we recover somehow? So let me just state the question. Can we recover somehow like these maps from any physics that you may observe from behind? So like, do you have any guesses? Do you have any hints of what's going on? Sorry.
I wanted to ask, when I get
Sure.
two same shapes out of this algebra, let's take for example as M0, M1 and M-Y,
Yeah.
I only get B1.
Yeah.
Are they the same?
I mean, they are equivalent.
Okay, they are equivalent. Okay.
I mean,
I only care about different.
Exactly, different shapes. I mean, that's because, I mean, whenever you have like these two algebras, if you compute the representations of those algebras, I mean, you're going to see that these two are something called Morita equivalent. I mean, so you're going to get the exact same thing. What we are interested in is when you have like different shapes altogether.
They only change by, like, not by the shape, but by a coefficient. Let's say I find something like B1 plus 2 by.
Yeah.
Would in that case,
well, I mean, like there things change. I mean, and that's why I'm asking, like, because, I mean, what happens, I mean, is there any guess? Do you have any guesses about how we can guess the structure maps? Because then, I mean, like that, maybe that depends on what kind of coefficients goes in there. I'm not sure. I mean, the thing is that let me just finish the sentence. I mean, like, we know different shapes, but we don't know if they belong to the same Morita equivalence class. And that's really like the next question that we need to finish in here. So, I mean, just to make sure, because for example, another, I mean, like in some of the examples I mean, Sam and I work out, it seems like we find something more than was already classified in some cases, in the near group case. But the thing is that we don't know if like that's actually something new, or is actually something which is equivalent, just that it has a different presentation. Sorry. Go ahead. I guess, yeah. I guess, yeah. Yeah.
The NIM-reps are like the Cardi states.
Yeah.
Sounds a little bit like me. You're asking like Cardi states preserve different subgroups of the bulk symmetry.
Yeah.
It's sort of backwards. The rough draft.
Yeah. Tell me.
I see the other board.
Oh, sure. Yeah. Is that okay? No. Nope. What would be your guess? Ooh, I'm a bit... I'm not completely sure how that would look like in here. Yeah. Wait, you're talking about NIM isomorphisms? Or like, I mean, because it should be, I mean, like, if I understand correctly, like tilting should be something fancier, but hey, I'm not, I really do not know much on that. But hey, maybe that's an idea. Yeah, sure. For the minimum models, we didn't, no, that was kind of, well, for some of the cases that were worked out before us, so like from this paper by Baron and Peters, and I mean, they compute some of the simplest, I mean, SUN at level 1, and then Gannon went on and on to other different biseminated models. So I think that's kind of sorted. That being said, in a different work, in a different thing by myself as well, we do have a classification of like what, well, not by myself, but we do have an ID classification for the minimum models of the algebra objects you can get. And I mean, like I mean, I haven't tried to get it back from the NIM-reps, but probably it shouldn't be too complicated at this stage. I really can't figure, Andy, if you're like excited or like confused. Okay. Yeah, let me just write down maybe the second question, so just let you. Okay. I'm not completely sure what else I wanted to say. I mean, in terms of examples, I mean, I can give you like some of the results we got for like pointed, for near group, not really enlightening, but maybe you're interested, I don't know. Where? Sorry, for which graphs? For like the NIM graphs? No, don't think that. I mean, like besides having some sort of functions or isomorphisms of, I haven't. Wait, I think I know where you're going. Yeah, no, I'm not sure. I'm not completely sure, but maybe that's something to check. I really get your point that I should be checking this as quivers. That I should be analyzing the NIM graphs as quivers. I mean, they do. It's just like there's many voices in my head when it's like, okay, you should try this, you should try that, and that's like one on the very back. But if you think that makes sense, okay. Yep. Yeah, I don't know. I have like, I mean, the last 5 minutes, I can show you a super slide on with some results, if that's okay. Which is like, boom, everything we classified, like fantastic, amazing, unreadable, as you may notice on the screen. But mainly this is telling you that for the case when, I mean, this case in here, which is a pointed case. So like when you had like your fusion ring is a group. I mean, you know that every reducible NIM-rep is going to be given, I mean, the basis elements are going to be parametrized by left causes of H and G. So like you have this shape, sorry, not exactly. This is the shape of your basis elements, and you're going to be able to jump to construct the graphs. And then, so the algebra objects are going to be given by these guys, and this H in here is the H that parameterizes the NIM-rep. The case of near group, if you're wondering, this is how the fusion ring works. It's a little bit more complicated. Actually, when we were working on this, we noticed that we could write this down in terms of matrices, and that problem was very, very not well known. So only some families of solutions can be found. And what we solved, it was for rank 1, so like these are just numbers. Get a similar thing to what we had in the group case. And in rank 2, we got something something also quite similar. Again, here the algebra objects arising were of this shape. Sounds familiar for icing. And then in the case of one quantum group, this one, A1L, at this level 1/2, we exactly found, I mean, that was something I really liked. When it happened, when we managed to prove that up to isomorphism of NIM graphs, we only had one admissible NIM-rep, and that corresponded to a theorem I had never understood. It was exactly that one. With the shape expected, which was a little bit more complicated. This was done by Ostrich and some time ago. And as I mentioned, I mean, like we match exactly, sorry, just let me finish the sentence. We match existing classifications that we knew. So it was like, boom, okay, this is the way to go. And using this, I mean, let me just finish by mentioning that, I mean, what we are doing right now, and hope to post a paper on the archive very soon, together with Agustina Senki from Southern California, Emily McGovern from Oregon, Melody Melander from Ohio, and Monique Muller, I mean, from the São João Federal University of Brazil. What we're trying to do is to use this procedure to study two generalizations of the Tambara-Yamagami fusion rings. I mean, I mentioned that they were quite relevant and actually have been used up and down in mathematical physics. So what we want to use the NIM-reps to classify what one can get from the different extensions, and then classify and see what the NIM-reps can tell us about that. But that's upcoming work, hopefully soon in your very close archive. And if we're good, we have been very good, Santa, hopefully before Christmas. Sorry.
I wanted to ask for the near group.
Mm-hmm.
The second structure that you showed, the second algebra, looks pretty much like the group one.
Mm-hmm.
The first one looks more like that. Is there any difference between the two? Like, is that the first one the one that actually differs from the group case for the pointed case?
Sorry, I'm not completely sure. Like,
yeah.
Mm-hmm. I mean, please note that we have, I mean, here we're specifying rank 1. Oh, sorry. Yes. Rank 1. Why you're not responding? Rank 1 and rank 2. So, because in rank 1, this is what you're gonna get. Then this is what you get in rank 2.
Mm-hmm. Because the way
Mm-hmm.
But is it any different or
Is it that? No, I mean, what?
like this?
I mean,
the result
in
X
yeah.
doesn't appear in the
Oh yeah, sure. No, yeah, because in this, I mean, in the rank 1 case, you need to account for the non-invertible. So when you go to rank 2, I mean, this non-invertible doesn't appear. Sorry, this is not. It's not working. For the, I mean, the rank 2 case, I mean, this non-invertible doesn't appear anymore. And in the case of, I mean, but in the rank 1 case, it just happens to be there. So like. Mm-hmm.
non-invertible.
Yeah.
Formally look like
Yeah. I mean, like you get exactly the same shape of the of algebras. I mean, like you have these algebras in here. I mean, on the pointed case, these are called the group. I mean, the group algebras. You get exactly the same thing here. So yeah, you.
non-invertible
Yep. Yeah. Thank you. Anyways, I think my time's up, and I really don't have much more. So I guess that we can leave it in there. Thank you. Thank you. You made me happy with all these questions. But yeah, and if anybody has like an intuition, like what's going on, the physics and all that, just drop me a line. The one with Sam, yes. I mean, the other one with the woman in mathematical physics collaboration, that should be coming very soon. I hope I don't jinx it.